Hi guys, welcome to my YouTube channel. Today I'm going to be going through Physics Unit 4, January 2021. As I solve the questions, I'm going to try and briefly explain some of the concepts, so I hope that you benefit from this video. Let's get started. So the first question is a multiple choice question, and the question says, which of the following is not a vector quantity? So we know that work done immediately is not a vector quantity, but however, if you did forget, then just try and remember the equations. For example, impulse is Ft, and F is force, which is a vector quantity. Now we know that vector is magnitude and direction, whereas scalar would be just magnitude. Most of your equation sheets will consist of the equations, so just make sure you know which ones are vectors and scalars. And yeah, so the second question says a particle of mass m has momentum p and kinetic energy ek. A second particle of mass m over 2 has a momentum 2p. What is the kinetic energy of the second particle? So we start by writing the equation, and we know the equation that links energy and momentum is E equals p squared over 2m, and this would be the one for the first particle. So let's say ek1. Now ek2 says that it has double the momentum, so I'm going to put that in brackets, and that would be squared, and has half the mass. So I'm just going to put whatever changes there are in brackets, and I'm going to compare them both. So just to break it down, let's expand this. So that's going to be 4p squared over m, and that's going to be half p squared over m. If you'd like, I feel like putting the numbers outside makes it way easier. So whatever kinetic energy or new kinetic energy value you want, put it on top and divide it by the original one. So that would be 4 divided by half, which would be 8. So the answer is 8 EK. In 2016, the element organocin was added to the periodic table. One isotope of organocin has a symbol 294, 118 OG. So 118 is the proton number, and the one on the top is the mass number, or the nucleon number. So which row of the table shows the number of protons and number of neutrons in the nucleus of this isotope? So the number of neutrons is just the mass number subtracted by the proton number. So mass number minus proton number gives you the neutron number. So we know that the proton number is here, so we know it's either A or B. And we know that they're trying to trick us. We might get confused whether it's 294 or 176, but we know 294 is the mass number, so without doing any calculations, or if you'd like, you could check it, we know that it's going to be 176 because that's the remaining of the mass number once we subtract the proton number. So the answer is A. Question number 4. A particle has a mass of 3.17 times 10 minus 27. Which of the following gives the mass in GeV over c squared? So we know that the equation is E equals mc squared. And a quick trick would be just to do the opposite. When you have kg, then just follow the rule that comes here in this direction. So it tells us to multiply by c squared. So I have, this is my mass, 3.17 times 10 minus 27, multiply it by the speed of light, which is c, 3 times 10 to the power of 8 squared, and divided by g, which is, or ev first, whatever order it is. G is 10 to the power of 9, which is giga, times ev, which is electron volts, which is 1.6 times 10 to the power of minus 19. And your answer would be D. However, if it was the opposite and they wanted you to convert it to kg, you'd just follow it in this order. You'd go from here to here, so you'd multiply your energy, which comes in this form, by giga, multiplied by electron volts, and divided by c squared. And that would give you kg. Question number 5. An uncharged capacitor, a resistor, a switch, and a cell are connected in series as shown. Which of the following shows how the charge stored in the capacitor and the potential difference across the resistor vary with time after the switch is closed? So we can tell that once the switch is closed, it's gonna get charged. It was initially uncharged, and these are connected together. This is the EMF, and this is the capacitor. So as we close the switch, the electrons from the negative terminal begin to flow into one side of the plate, and on the other side of making it a negative terminal, and on the other side of the plate, the electrons start to leave, so it becomes positive. And this is how the capacitor is charged. So let's take a look at these graphs. Now the charge as the capacitor is getting charged will increase across the capacitor because there are electrons that are filling up the plates, obviously, and the PD across the resistor will begin to decrease. So obviously it has to be C. The reason why PD across the resistor decreases is because the PD across the capacitor begins to increase, and since they are in series, the EMF equals the voltage across the capacitor plus the voltage across the resistor. So as it begins to charge, the PD across the capacitor increases, and hence the PD across the resistor decreases. And the current decreases. It's not part of the question, but the current will start to decrease. Question number 6. A positron and a muon travel at the same speed through a magnetic field. The magnetic field is directed into the page. Into the page will be a dot, so it's going in. Which of the following diagrams best represent the motion of the particles? So, first of all, we could use the equation R equals mv over bq to know which path would each particle take. And why we need this equation is to just remember the proportionalities between mass and radius. So the bigger the mass, the bigger the radius. So this would be the bigger radius, or this would be the bigger radius. So the ones that just in general have that bigger radius have the bigger mass. Now we know that in the first generation particles, we have positron, or really we have electrons, but positrons are the anti matter of it. So positron is in the first generation, and in the second generation we have muon, which is heavier. And so just an extra note is that is why it took longer to find muons, because they are heavier and more unstable, And so electrons and positrons were discovered before muons. So we know that muons are the ones that are going to be taking a bigger path, or a larger radius. They'll have a larger curvature. So the answer is either going to be C or B. Now, for the direction, we'll need to use Fleming's left-hand rule. And remember that muons are negative and positrons are positive. So when doing Fleming's left-hand rule, we need to remember that it only works for positive, and the result we get, we should reverse it, and that'll give us the result for a negative charge. So we can start with the positive. We can check if B is the answer. I'm still not sure if it is. So if the magnetic field is into the page, make sure to only move your wrist and not your fingers. That's a problem that students sometimes fall into. So put the magnetic field is directed into the page, and since the particle is moving this way, and so we know, like, for the centripetal force is towards the middle, so towards the center, so the force is this way, and so the velocity should be that way. And that doesn't look like it, because imagine if I threw the charge upwards, then it would go like this, and then because of the magnetic field, it should start a curve. So that shouldn't be the answer, because the velocity that was given due to Fleming's left-hand rule was in the opposite side, and a positron is a positive. So B is not correct, and C would be the correct answer. And just to check again, if you wanted to check with the positron into the page, we know that the velocity is this way, and here the force goes that way, and so we know that it's correct. And with a muon, if you wanted to check, because it's negative and you weren't familiar with it, here is into the page, the velocity is this way, but it claims that the force should be that way. However, it is moving this way, so it's negative, and we have to switch the sides, and so it's correct. A trick if you struggle with Fleming's left-hand rule sometimes with moving charges, if it was a negative charge that was moving clockwise, then the magnetic field is into the page, and if it was a positive charge and it was moving clockwise, it's out of the page. Like, magnetic field is out of the page. So just try and fix it to your situation, but that's just a very quick trick to use if you wanted to check or if you were unsure. Question number 7, point charges of 2 microcoulombs and 3 microcoulombs are placed 1.2 meters apart as shown. What is the electric field strength at the point labeled X? So because there isn't a negative sign, we know that it is a positive charge here and here. And in an electric field, the direction of the electric field goes away from the positive charge. So we know that it goes towards X here, so to the right, and here it goes to the left because away from the positive charge. So what is the electric field strength? So they're opposite directions, so obviously we have a minus going on here, or subtraction. And we know that the electric field strength equation is F equals KQ over R squared. So KQ1, KQ2, sorry, and so electric field strength is KQ over R squared, okay? So K is just 1 over 4 pi A epsilon, and so this equation would be the charge of that, which is 3 times 10 to the power minus 6 divided by its radius. This charge away from x, it's just 0.8, and this charge 2x, and the distance between this charge to x is 0.8, and the distance between this charge and x is 0.4. So using this equation, would say 3 times 10 to the power of minus 6 divided, it's either this one or this one, I'm sorry about that. Okay, so for this question, it says point charges of 2 microcoulombs and 3 microcoulombs are placed 1.2 meters apart as shown. What is the electric field strength at the point labeled x? So the distance between this charge is 0.8 and x is 0.8, and the distance between this charge and x is 0.4. Now we know that the charge is positive in both because we can't see a negative sign, and we know that in electric fields, the direction of an electric field goes from positive to negative. So it's away from the positive charge, and so we draw arrows towards the x because it's away from positive. This is obviously going to be a subtraction equation, because they're in different directions, so right and left. So it's either B or D. Now we know that the equation for electric fields is E equals KQ over R squared, K being 1 over 4 pi epsilon, which is the free space permittivity, the permittivity of free space, sorry. And so if we use this equation, we know that Q is 3 times 10 to the power minus 6 divided by 4 pi epsilon times R squared. And as we discussed, R should be 0.8, and this is wrong, and this should be the correct answer. Now, question number 8. A wire is held firmly in place between 2 magnets mounted on top of an electric balance as shown. The reading on the balance is 1.5 newtons. The magnetic flux density between the magnets is 0.07 Tesla, which has the symbol B. When the wire is connected to a circuit, so there is a current in the wire, the reading on the balance is 1.503 newtons. Which of the following gives the current in the wire in ampere and its direction? We know that the equation is F equals BIL sine 90 and sine theta, but this is 90. The magnetic flux density and the current has a theta of 90, and so sine 90 really equals 1. So we can just say that the equation is F equals BIL, and the B is 0.07, sorry, and I is, what is I exactly? Oh, we need to find I. Okay, so I would be F over BL. So what is F? F is 1.503 newtons. And I'll tell you why in a minute. So that is F. And it's obvious because it's newtons, so that's a force. Over the magnetic flux density multiplied by the length, which is in the magnetic field, which is 5 centimeters, converted into meters, divided by 100. Okay, so the answer should be A or B. We need to now figure out whether it's X to Y or Y to X. Now, where did this number come from? So once we switch the circuit on and the current flows in the wire, the magnetic field acts on the wire, because when there's a current in a magnetic field, there's a force on it, on the wire. So once the magnet exerts a force on the wire exerts a force on the magnet. So we have a reading on the balance. So this is due to Newton's third law, and it's equal. So that way we can find the magnetic force that the magnet exerts on the wire. So as we know, since we know that it exerted it downwards and we had that reading on the balance, we know that the force is upwards, because the force here is the magnet to the wire. Okay, so using Fleming's left-hand rule, we know that the force is upwards and the magnetic field is this direction, because the magnetic field is from north to south. So the current should be from X to Y. So the answer is 8. Question number 9. A 6-volt battery is connected across 2 parallel metal plates. Which of the following shows the electric field lines and equipotentials in the region between the plates? Let's eliminate some answers to start with. So obviously we have discussed that the electric field always goes from positive to negative, and so this goes from negative to positive, so this is wrong, so it's either C or D. When we look at metal plates, we consider that, this is a 6-volt battery. So we know that from the negative terminal, from the positive terminal to the negative terminal, the positive is higher than the negative by 6 volts. So we can tell that it should be decreasing as it approaches the negative. So the answer is D. However, don't get confused with electric fields. The electric field is constant. So a charged capacitor is connected across a resistor of resistance R, and the current in the resistor is measured. A graph of Ln, current against time, is plotted, and the gradient of the graph is determined. Which of the following gives the capacitance of the capacitor? So first of all, let's write the initial equation that we know, which is I equals the initial I, E minus T over RC. This is the discharging equation. Then let's turn it into the ln form, which is ln I minus T over RC. Ln I equals ln I minus 1 over RC times T. We want to turn it into a form in which we can begin to compare it with the equation y equals mx plus c. So if this is y and this is x, then this will be m, because that's connected to x, because the form is y equals mx plus c. So this is m and this is going to be c, but really we need the gradient, because the gradient contains the c, which is what we need. So if the gradient is m equals minus 1 over RC, let's rearrange the equation. Minus 1 over m equals RC. So minus 1 mr equals c, or just you could say gradient. So the answer is B, because minus 1 divided by the gradient times r gives you the capacitance. And that's it for the multiple choice questions.